morning, everyone. We are the 2015 ASHRAE Applied Engineering Challenge team. I'm Leana Tran-Le.
I'm Minh. I'm Alolong.
And I'm Joseph Barnes.
A few of the things we're going to be touching on today are the specifications of our project, the calculations behind the design, the final design, and some of our testing results. So for our senior project this year, we decided to enter an ASHRAE competition called the Applied Engineering Challenge. And this year's challenge was to design a emergency shelter for heat illness victims. So the system, we hope that the system will delay and reduce the effects of heat illness for outdoor working professionals such as construction workers or workers in the agriculture field. We're following the ASHRAE standards with all of our design and our calculations, and we're keeping mind of all social and economic impacts locally and globally. So some of the specifications of the design is that it has to work in two environments: Sacramento, which is high temperature, low relative humidity, and Atlanta, which is mid to high temperature and high relative humidity. The shelter has to be assembled within 10 minutes, and within the 10 minutes after that, reach our goal temperature range of 68 to 75 degrees Fahrenheit and a relative humidity of 30 to 60%. It should accommodate for the 95th percentile body of construction workers in the U.S., and it should be able to be stored in a 3-foot cube box and weigh no more than 150 pounds.
So we started our research by looking to see what type of work had already been done in the market. And the first area that we went to was the shelter itself. And the three main types of shelters that they have on the market now are the vestibule, which is basically like a counterweight method in which the tent kind of unfolds on itself and uses counterweight to hold itself up. There's also an inflatable method in which air is pumped into the tubes to inflate the tent. And then also the accordion method, which is kind of like as an accordion would, it would like fold open and close. So some of the advantages of these are that they require little input energy from the person building it to erect the tent. And they also completely fold up and store into a really small space. There is also the exterior fabric, which is integrated into the structure, which saves a lot of time. But some of the disadvantages are the height and weight, and it costs a lot. And some of the assemblies can be confusing and time-consuming when you build it. And also, if the inflatable tent, if it somehow ruptures, then it would be useless, and that's not good.
So another area that we also looked into is dehumidification, and one such process is to use desiccants. So desiccants take moisture out of the air through a physical or chemical reaction. As you can see here, the physical reaction is a reversible process, whereas chemical reaction is basically reversible. So the benefits of using desiccant tablets is that it's easy to use and is very portable. But the problem though is that with the amount of moisture, if the amount of moisture is a lot more than it can handle, we need to add more desiccants into the system, which means it adds weight, so which isn't really a good solution for our system. And it's also one-use only.
So to continue with Frank, as we focus on the physical dehumidification option, there are two methods of physical dehumidification. The first one is a reusable desiccant wheel. Basically, in this method, the air gonna flow through the rotation wheel, and then it comes out drier and a little warmer. But this device using the method is not very common in the market. So we choose the cooling method, which is exactly the same mechanism like the regular air conditioning unit. And moving along, we have to deal with the cooling method. According to the psychometric charts, there are only two cooling methods. The first one is the evaporated cooling. In this method, the hot dry air, after going be in contact with the water vapor, it can absorb some water vapor and become cooler. However, this method is it has more disadvantages than the air conditioning method because the temperature is not going to down as the other method. And besides, we have to carry a lot of water too. So we're gonna choose the regular AC, which include the evaporator coil and the condenser unit to cool the air. And we need to site the AC unit for both places. The first place is Sacramento, which is hot and dry, second way is the Atlanta, which is a little bit less hot and more humidity. Because Sacramento has the hottest record, they go up to 106 and 73 relative humidity. So we're going to sign the AC unit, especially for Sacramento. But the dehumidifier will take care of the Atlanta case too. So as you see on the graph, and temperature of Sacramento can go up to 106 in some hot day. And talking about the theory, how to design the AC unit, there are four main heat loss we need to take into account for. The first one is the body heat coming from the person inside the tent. The second one is to cool the air inside the tent. The third one is we have to deal with the ventilation loss. And the last one is the cooling loss from convection, conduction, and radiation. And there are some simplified version of the equation according to each different type of cooling loss. And after summing all the cooling loss together, we got the total cooling loss is about 10,900. And to account for the 50% of the safety, it go up to 12,000. However, on the market, we're going to choose the 14,001 because it's available and it's higher in the power. And beside for the dehumidifier, there are two main equations right there. This one, simply the air, the air equation, and the second one is just the mass equal to density and volume. And the size for the dehumidifier is 45 per day.
So for our prototype design decisions, we decided to use the air conditioner and the dehumidifier and opted for a tent. So as you can see here, we decided to use a series of parallel layout. And for our air conditioner and our dehumidifier, we decided to let our cooling system to weigh the most out of our system. So as you can see here, it's 65 pounds and 14,000 BTUs like Minh mentioned. This also has a 3 fan speed and dehumidification. As for the dehumidifier, it's 25 pounds. So altogether, the cooling system weighs around 90 pounds. And also, this meets our sizing limit. And like Minh mentioned, 40 pounds per day to dehumidify. And then as for our shelter, this fits about a person of a 7-foot relative height. And then it's easy to set up, but the problem though is that we also have to reach inside the tent to close the window to make it usable for our system. And also later on, we came down to using a down feather comforter and a mylar sheet to deal with the heat transfer with the outside conditions. So for our final design, we went with a series option. As you can see here on the right, that's what our tent looks like right now. And for the assembly, what you want to do in terms of the emergency, you want to turn on the air conditioner and dehumidifier first to get it operating and stabilized, and then you open the tent because it needs some time to open up. And then, as you can see with the colors, you just assemble everything together as shown. And then you have what the trick is for the AC outlet to go into the tent. That needs to come in at a certain angle inside the tent so that it hits the victim directly. And then for the duct that connects to the tent and the dehumidifier, that needs to be secured from the tent entryway with a zipper.
So the next area was the microcontroller and electronics system. It's broken down into 5 steps. The first step is there's several sensors inside the tent that measure the temperature and humidity within the structure. And then the sensors send that information to the microcontroller. The Arduino microcontroller processes the information based on a very long program that we've constructed for that. And the microcontroller acts as the brain, and it decides whether or not the system will either turn on the air conditioner, turn on the dehumidifier, or shut each one of those off. And then once the thermal conditions are controlled, then the Arduino will turn off both the AC and the dehumidifier. So here's a really quick picture of it. Here's the Arduino microcontroller right here. This is where the input comes in from the sensors, and also down here. And then through the wiring, it basically goes out and controls the air conditioner.
To create more safety for the person laying inside the tent, we're going to do a redundant control method, which use the wireless ASHRAE. And in this method, we use some main component parts, which is the ASHRAE device and the Arduino board, the relay power switch, and the temperature and humidity sensor. So we are going to control the system based on the temperature parameter only. So here is the two control diagrams that according to the wireless method. On the left side is the relay side, which includes the relay and the Arduino Uno, the ASHRAE wireless, which are going to receive the signal from the sensor side. And the sensor side has the Arduino Mega, the sensor, and the ASHRAE module going to send signal to the relay. And then the relay power switch going to turn on and off the AC. We're going to show you guys later after.
So this is an example that we changed instead of, so this is the box that goes in, this is the sensor package inside of the shelter. There's a temperature and humidity sensor on there. We changed the programming so if you get the temperature high enough on the sensor, the light will turn on. So it's wireless technology to the light. Okay, so now that we've done our design and we've chosen our final, or now that we've done the calculations and chosen our final design, we have to go into testing to verify that everything works out. So we built a testing structure around our design, our final system, which is a 5-foot tall, 8-foot wide, and 10-foot long rectangular structure that we wrapped in plastic sheeting so that we can simulate the conditions of Atlanta and Sacramento. We put in 5 space heaters in there to get the temperature up to 106 degrees when we were testing for Sacramento. And when we were testing for Atlanta, we added a tea kettle to increase the relative humidity inside the space. So here's our testing results from Sacramento. This is the initial result. And on here, to get to the 75 range that we specified, it took 30 minutes, which is 10 minutes over what we were hoping for. So we kept fixing the design and finally realized that the reason we were taking so long to get the temperature down was that we were losing a lot of cold air through the tent material because it's a really thin porous nylon. So we added the insulation that Frank touched on earlier, which was a layer of down feather blanket and then a layer of mylar over that. And then we went over to test for Atlanta. It took about 3 minutes to get into the range of relative humidity that we wanted, which is good, really fast. We weren't able to get into the range of 75 degrees for temperature, but we'll talk about that later in our conclusions.
So here are the conclusions. The single system functioned both successfully in both Sacramento and Atlanta. We were successful in getting the temperature from 106 degrees down to 75 degrees in about 8 minutes, which was pretty good for under 10 minutes. However, it did require additional insulation, as Leana mentioned. Testing for Atlanta, we were successful to get the humidity well below 60% in about 3 minutes, so that worked out very well. The initial set time, the setup time that it required to open the tent up and connect all the ducts to the air conditioner and dehumidifier took about 2 minutes for me, but I was experienced with it, so we had someone else come in that had no experience on it, and it took them about 3 to 4 minutes to test it up, so that was well below the 10 minutes again. The system was also sized perfectly for a 95 percentile body weight and body size, which was about 6'4" and 204 pounds. And the system constraints and the reusability of the system was met. We weighed each component individually, and it came out to be about 96 pounds, so that was well below. And it was also able to fit within the 3-foot cube. So some future work and improvements we can make on it. We want to work with the AC and dehumidifier manufacturer to see if there's a way that they can combine both systems together to kind of save some space and some weight. And we also want to see if there's a way that they can make the ducts fit perfectly with the 4-inch diameter ducts that we have to supply the air, so we don't have to create the connection. We also wish there was a better way to measure the fresh air. The percent that we came out to be was about 5% that we needed for our design, but it was very hard to measure based on all the ventilation losses. So that would be another area. And we also wanted to design a tent where the insulation was fabricated into the tent, so we didn't have to worry about insulation losses. There are some references.
Let me touch up before. For future work, I was saying for Atlanta case, we weren't able to get the temperature down to where we wanted. We checked our dehumidifier, and the air coming out of the dehumidifier after it was being dehumidified was around 140 degrees Fahrenheit, which shouldn't be that high. The dehumidification process shouldn't be raising the temperature an extra 30 degrees. So we think that the unit we had was defective, but we didn't have the time or the funding to replace the unit. So we're hoping for future work we can replace it and verify that last, see if we can get the temperature down for Atlanta. Some of the people that helped us out in our project this year, Dr. Nicole Okamoto was our advisor. We had Justin Leve. He helped critique our design in the beginning of the first semester when we were still at a loss of how to design the project. Sargon Ashea, he helped us understand the ASHRAE standards. We used a bunch of books with a lot of reading, a lot of tables. We were really lost with that too. And then the Associated Students of San Jose State for funding our project. Thank you. Anybody have any questions?
Oh, I do. How did you measure the CFM of this system?
We used the CFM coming out of the AC unit, or?
Yeah, we used the wind speed anemometer, which you see right here. And based on what this measured is just the velocity. And so we took the velocity and multiplied it by the area of the duct, and that's how we found the CFM.
That's interesting. Thank you.
Any other questions?
Did you actually test this with someone inside the tent? Yeah.
Each time we tested, there was always a
Oh,
body
okay.
inside the tent, so we could simulate the same heat load if there was like a heat illness
Hmm.
inside.
Cool.
Right, so in continuation, in addition to that, we also tested, the reason why we decided series the layout was better than parallel was because it outperformed the parallel layout. We really beat our numbers to do that.
Cool.
So your guys' temperature that you took over time, was that like assuming like that's where the person's gonna be that's inside, or is that, where was the temperature?
The sensors?
Oh,
That's-
it's from the sensor.
Yeah, there's
Oh, okay.
several sensors located inside the tent, and the programming actually takes the average temperature reading from the sensors.
Using the different microcontrollers, did you guys run into any programming problems trying to like make it compatible to each different type of?
It was very difficult, especially with the temperature sensor, because the sensor measured the humidity and temperature both on one output. So we had to figure out how to decipher based on that, how to kind of gauge that.
First, I always have to ask this one question. So for the ventilation, what was your estimate of ventilation?
Amount of
Is that-
CFM coming out.
Is that the requirement for the ventilation?
Yeah, just because you had mentioned you wanted like 5.7 CFM or something like
Yeah,
that.
in the calculations we calculated for 8 CFM, but when we used the wind meter, I can't remember the number, but it was way over, right?
It was closer to about 100.
It's in our final report, but I can't remember the number off the top of my head.
To prove that, you just need to measure the air velocity before entering the tent and after you enter outside of the tent. So we will minus the two numbers, the difference. You know that the ventilation volume, the air is over than 8 CFM, so it's more than the requirement.
Any final questions? Well, thank you very much.